All right, today we're diving into something truly wild. It's a scientific proposal that mashes together biology, quantum physics, and topology. Yeah, it's a mind-bending combination, so let's just jump right in and see what it's all about. I mean, it really does sound like the setup to a pretty nerdy joke, right? But it's not a joke. It's actually the key to a revolutionary new kind of technology. This idea pulls these three completely different fields together to tackle a huge problem in the world of modern sensing.
Okay, so what is that big problem? Well, it really all boils down to a classic challenge, trying to hear a tiny, tiny whisper in the middle of a hurricane.
Just imagine you're trying to tune an old radio to a really distant station, but all you can hear is that shh, that static. Well, in the quantum world, that kind of static is everywhere. It's, heat, electrical interference, just a constant background hum of noise. And this noise is so loud that it completely drowns out the incredibly faint magnetic signals we're trying to detect. So the big question is, how on earth do you filter all that out?
So the first piece of the puzzle for solving this, it's something pretty remarkable, and it comes straight from the world of quantum biology. The key technique is called optically detected magnetic resonance, or ODMR. Now, I know that sounds super complicated, but the idea behind it is actually beautiful. See, scientists have discovered these amazing proteins whose quantum state actually changes depending on the magnetic fields around them. ODMR is just a clever way to shine a light on these proteins, and then by looking at the light that bounces back, we can read their quantum state. It is literally like having a compass the size of a single molecule that you can read with a simple flashlight. How cool is that? And this is where it gets really exciting. This is the part that's a total game changer. These little protein sensors are not only super sensitive, but, and this is the big one, they work at room temperature. They can even work inside a living cell. You don't need any of that giant, expensive, supercooling equipment you usually associate with quantum stuff. This basically makes quantum sensing compatible with biology for the very first time.
Okay, so now we have our tiny sensor. Great, but a sensor isn't much good if you can't actually move it to the spot you want to measure, right? For that part of the solution, we're going to turn to one of nature's most amazing little creatures.
Say hello to magnetotactic bacteria. Yeah, these microorganisms have a literal superpower. They build their own internal compasses. Inside their bodies, they create these tiny little chains of magnetic particles. This chain acts just like a compass needle, and it actually forces the bacterium to line up with the Earth's magnetic field and swim along its lines.
So get this, these bacteria aren't just floating around randomly. They're active, self-propelled swimmers. You can think of them as nature's own microscopic, self-driving drones, always on a mission to find and follow magnetic fields. So what happens when you combine our quantum protein sensor with these little living navigators? Well, you get the perfect biohybrid, a living, swimming quantum compass.
Okay, so we've got the sensor and we've got the vehicle to carry it, but we still have that original problem, remember? The noise, the static. The final ingredient to solve that is probably the most mind-bending part of this whole thing, and it comes to us from the world of pure math. The answer is in a branch of math called topology. You've probably heard the classic example, right? That to a topologist, a coffee mug and a donut are basically the same thing. And that's because you can kind of squish and stretch and mold a donut shape into a coffee mug shape without ever ripping it. The one thing that doesn't change is that single hole. And it's that focus on properties that don't change that makes topology so incredibly powerful for our problem. So here's the wild idea. The proposal is to build a microscopic channel for our bacteria to swim through, but with a special twist, literally. The channel has a single half twist in it, just like a Mobius strip. And that one little twist gives the channel a very unique topological property. It's not just a racetrack anymore. It's a space where if you complete one full lap, you end up flipped. Your whole orientation changes. And this is the genius solution to the noise problem. Instead of trying to measure some fuzzy, wobbly, continuous signal, we just count laps. That's it. 1 lap, 2 laps, 3 laps. All those little bumps and wiggles from the background noise, they don't matter. They can't change the number of laps. A bacterium has either finished a lap or it hasn't. It's binary. This topological hash, as they call it, turns a messy, noisy, analog problem into a clean, simple, digital one. All right, so let's put all three of these amazing pieces together and see how this incredible device actually works. It's actually a pretty straightforward process when you break it down. First, you take the magnetotactic bacteria and you equip them with that special light-sensitive quantum protein. Step 2. You introduce these little biohybrids into that twisted micro-racetrack. Then, as they start swimming along, guided by a magnetic field, all we have to do is watch them and count the laps. And that final number, that simple, clean count, that's our measurement, totally free from all that fuzzy noise.
And you can really see the difference when you look at the kind of data you get. A standard sensor gives you this messy, wavy line where the real signal is buried in all the noise. But our topological sensor, it just gives us a number. 0, 1, 2, a clean digital output. The noise is still there, bumping the bacteria around a little, but it just doesn't matter. It has no effect on the final lap count.
So just how much better are we talking? Well, the main goal here is to drastically cut down something called the bit error rate. That's really just a fancy way of saying how often the sensor makes a mistake because of noise. In a normal, straight channel, you'd expect a pretty high error rate. But with the twisted Mobius channel, the whole point is to make that signal way, way cleaner and more reliable.
And they have a very specific number in mind. The project is aiming for at least a 50% reduction in errors compared to a standard channel. That's the bar they've set for success. Look, this is obviously an incredible piece of science. But what's the bigger picture here? What's the long-term impact? Why should we care about this outside of a high-tech lab?
And I want to be clear, this isn't just some cool pie-in-the-sky idea. It is a full-on engineering plan. The proposal has these really strict, measurable targets for everything, from the clarity of the signal all the way down to keeping the temperature stable to within a tiny fraction of a degree. This is exactly how groundbreaking science gets turned into real, reliable technology.
The potential impact here is just huge. If this works, it could kick off a whole new era of quantum sensors that are affordable, tough, and, again, worked at room temperature. It's building a real bridge between the, let's face it, weird world of quantum physics and the warm, messy world of biology. This could let us look at what's happening inside living cells at a quantum level in ways we've only ever dreamed of. And all of this really leaves us with a pretty profound final thought. By taking living things and turning them into our most advanced sensors, we're doing more than just building a new tool. We're actually changing the way we think about technology and nature. It makes you wonder, right? What kind of secrets could we uncover when our instruments are actually alive?